So we still have a few things to talk about as far as electronic configurations is concerned. So here we'll deal with noble gases and ionic configurations, and there is some other stuff too. Okay, so let's get started. So in this one, okay, how we will do for ions, we will learn about core electrons and valence electrons also. Okay, that's where we're going to get started. So just a review over here, don't forget that you have the S block, the P block, the D block, S1, S2, right? P1, P2, P3, that's how it goes. Shell numbers are 1, 2, 3, 4. That's how it goes. So just kind of reminding you of that. So let's talk about valence electrons and core electrons. Valence electrons are the outermost electrons, okay, found in the valence shell. What is the valence shell? Outermost shell of any atom. So I will have to ask you to determine the valence electrons and core electrons for elements. So how are you going to do that? So for some of the things, it's going to be really easy. Okay, for main group elements is super easy. Okay, the group number is the valence electrons also. So group 1 has 1 valence electron, group 2 has 2, 3 has 3. It doesn't get simpler than that. Okay, that's for the main group elements, because as you're filling out electrons, you're filling out the outermost shell. Okay, why are you filling out the outermost shell? Because that's the lowest energy electrons in there. Whatever is inside is then the core electrons. Okay, so the outermost shell is the valence shell, which has the valence electrons. Everything else inside is core electrons. So let's look at here for phosphorus. So phosphorus is in group number 5, so you don't even need to think. You're like, okay, group number 5, 5 valence electrons, that's it. Okay, and it has 15 electrons. So if 5 of them are valence, then 10 are core. But let's see how to look at that in a configuration. Okay, so here is the electronic configuration for phosphorus. When you want to figure out the valence electrons, the main thing you need to focus on is the shell number. The shell number should be the highest number, okay, which is the N number. So here, everything, the highest shell number, which is 3, so every electron in that highest shell number is the valence electron. Everything else is core. Whether it's the first shell or second shell, it doesn't matter. Everything else is core electrons. Okay, that's how it works. Here is another example. This is for selenium, and now I wanted to include the d electrons also, because of course we have the d orbitals as well. Okay, so here is the configuration, and I want you to focus on, again, the highest shell number. When we write electronic configuration, we write it in the Aufbau principle manner. So lowest energy first, that's what we do. But when you're trying to find the valence electrons, then you're looking at the highest shell number, not highest energy, but highest shell number. So you look at the N number, and here it is 4, here also it is 4, so which means 4 plus 2, that's 6 electrons, okay, for selenium. Now you could have looked at selenium also normally and said, okay, selenium is in group number 6, so it's going to have 6 valence electrons, and you would be fine. Okay, but I did want to go over the d electrons here with you. Okay, so you don't mistake this as part of your valence electrons. It's not. Okay, it's always the highest shell number. You write the d because of the Aufbau principle. Okay, again, I don't want to talk about it too much to confuse you, but you know, that's how you write. So that's how it is. So once your highest electrons are taken away, which means that the largest shell number is taken away, everything else is core electrons then. Okay, that's how you do valence and core electrons for any element. Now the noble gas configuration, this is like the best thing possible, okay, for us. Now noble gas configuration is when you are writing electronic configurations for so many electrons, okay, like we did iodine before, right? And so when you write electronic configurations for so many electrons, you don't want to keep writing all of it all the time. So what chemists do is that they chop it down, okay, into saying that, all right, I'm going to fill out, let's say, 18 electrons of argon, and then after that, I'm going to fill everything else out, okay? And that's the noble gas configuration. So whatever element you have, you take the previous noble gas element, and then those electrons are accounted for, and then you fill the rest of them out, okay? So, for example, when you're filling for tin is 50 electrons. Okay, so you have 50 electrons in there. So for 50 electrons, xenon is 54. So it means you can't choose 54. You have to choose the element below before that. So you will choose krypton. So which means 36 electrons are accounted for, and then now you're going to fill the rest of them out. Okay, so it makes your life a little bit easier. And this has nothing to do with the core and the valence, by the way. Okay, this is completely different, so don't confuse the two things. Okay, noble gas configurations, you are just taking the noble gas before the element. Okay, that's all it is. So for example, if you're filling for chlorine, which has 17 electrons, 17 means you cannot use argon, you have to use neon. Okay, for arsenic, which is 33, you're going to use argon for that. So how do you write this kind of electronic configuration? I've given you a couple examples here. So bromine, the complete configuration is given here. Okay, this is the complete configuration. Bromine is 35. So for 35, you would have to use argon. So here is argon, so which means that 18 electrons are accounted for, and you're going to fill out the rest. So which means after 18, you go to the next shell, and the next shell is 4s2, and then you fill out the 3d10 and 4p5. Now, again, this doesn't change anything about the core or the valence electrons. Okay, this is just about writing noble gas configurations. That's all it is. For tin, which I said over here, so tin, which has 50 electrons, so for 50, you're going to choose krypton, and then the rest of them you're going to fill out. So for tin, the configuration is going to be krypton, and then 5s2, 4d10, 5p2. When you're doing noble gas configurations, please mind it that the question should ask for it, okay? Because I ask you sometimes to write the complete configuration, okay, for noble gases. So, sorry, not for noble gases, for elements, okay? So I want you to write the complete configuration. I don't want you to take shortcuts all the time, but in some cases you have to take shortcuts, all right? So for yourself, you can do it, all right, but not for me, okay? If I ask you for complete configuration, you got to give me the complete thing, okay, over here. So of course, let's look at a problem of core electrons and valence electrons. So again, sit with your periodic table. That will really help you. So let's look at the first problem here for core and valence electrons. So it says for A, 1s2, 2s2, 2p3. So we're going to count only the highest shell number. So that is 5. So that's 5 valence electrons. Okay, that's how it works out. For arsenic, you need to look at the periodic table. Arsenic is in group number 5. So if it's in group number 5, 5 valence electrons, you can probably tell by now, VE, valence electrons. Okay, and then zinc. So for zinc, which is a transition metal, it might be a good idea to write the configuration. Okay, so once you write the configuration, then you can see that the highest shell number is 4. Okay, in this one, so there are 2 electrons only in the valence shell. All right, so that's the answer. For chromium, and chromium is also transition metal, so better to write out the configuration for this. And this one you have to be careful because for chromium there is an exception, and you have to fill the D first, right? So when you fill that, you only have 1 electron left in the valence shell, which is the 4s1 electron. Okay, so be careful with all of these things. You don't be in a rush, okay? Because chromium is not going to be 6 electrons, okay, for example. So just don't be in a rush. Don't count just the last electrons and be done with it. Identifying the noble gases, I think this is probably the easiest assignment for any chemistry course. So here for aluminum, look for aluminum, which is 13. So the one before that is going to be neon. I hope you're sitting with your periodic table. For germanium, which is 32, it's going to be argon, which is 18. For iron, iron is 26. So for iron 26, it's also going to be argon, which is 18. And for bismuth, and bismuth is way down, way down, okay, and that's 83. So xenon is the best noble gas for that. Okay, so just look at the periodic table to get your answer for which noble gas you need. Okay. Let's look at the configuration for ions now. So there are two kinds of ions, cations and anions. Cations give electrons and anions have accepted electrons. So for the main group elements, it's pretty easy. You just take the last electron and you take it out. So for example, in aluminum, this is your electronic configuration. The last electron that you filled out is what you take out. Okay, so the last shell, all of the valence shell electrons, that's what you take out. So you don't take out from the core electrons, okay, only from the valence shell you remove those electrons. So that's what you would do if you had a main group element. Okay, again, last shell. For transition metals also you have to do the same thing, okay, which means that you have to remove from the valence shell first, then you go into the core. Okay, so for Sc and then scandium plus, which means just a monocation, if you're removing only one electron, you will remove it from the s orbital here, because that's in the fourth shell. You will not remove the last electron because that's actually core electron. So you don't remove that, you remove the valence shell electron first. So 4s2 becomes 4s1. Okay, that's what happens with transition metals. So start with the fourth shell, then you go to the core. When you go to the core, then you start with the d electrons. Okay, that's how you do it. For anions, you just add to the last empty subshell, and again it is in the valence shell. Okay, and generally when you're adding electrons, remember anions are formed by the non-metals, which are on the right hand side, which means it's generally going to be the p subshell. Okay, that's where you're adding electrons. So you're never really removing electrons from the p because they never give electrons, you know, non-metals never do, but still, anyhow. So anions, like for example sulfur, if it has 3p4 as the last electron shell that you filled out, then the sulfide, the two electrons you're adding are going to go on to the p orbital. There is no other space there, right? There's no other space. So you fill it in the last electron shell. So that's how you would do the configuration for ions. Let's look at some examples, okay, for writing the configurations. So write the SPDF notation of the following ions. So you have calcium. So I've written the original configuration also here for you. So you can see that we are removing for calcium 2 plus the last two electrons, okay, which is also the last shell. Main group is very easy, okay. Main group you are a little bit easier to deal with, you know, with removing electrons. It's the transition metals you have to watch out, okay, a little bit. So for calcium, the two electrons you're going to remove is this fourth shell electrons. The 4s2 is gone. So then this is the configuration. For iron 3 plus, now iron is a transition metal. So here is the electronic configuration. So again, remember, remove 4s2 first. All right, that is the valence electrons here. So remove the valence electrons. And then since this is 3 plus, you're going to remove one more electron from d orbital. Okay, not from p, from d, the higher energy, okay, from there. So then this is going to be your configuration. Manganese 4 plus, another transition metal. So here this is the configuration, and so we have 4s2 3d5. So for 4 plus, we're going to remove these two electrons from the fourth shell, and then we need to remove two electrons from the d shell. Again, don't touch any of that until you remove all the d electrons. Okay, so 3d3. And then bromide, which is one extra electron. So here is the configuration for bromine, and then when you add electron, you electron in the last subshell, okay, possible in there. So those are the electronic configuration of ions. Now I want to show you something that you will see. Let me see if I have it here. No, I think it's in the next one. Okay, so here's the one for core and valence electrons. And so now we're looking at the core and valence for ions, okay, not for elements. So for calcium ion, I've written the original configuration also over here. So it's crossed out, but you know, the original is still there. So 1s2, 2s2, 2p6, 2s2, 2, 3p6, and then 4s2. Since calcium is 2 plus, you're removing 2 electrons. And again, you remove from the outermost shell first. So 4s2 is gone. Okay, so once the 4s2 is gone from the outermost shell is now the highlighted one. Okay, the 3s2, 3p6. So that's the 8 valence electrons now, and the core electrons are going to be 10. So the s2, 2, and then there's 6 over here. Okay, so that's 10 core electrons and 8 valence electrons. Main thing is knowing which electrons to remove and where to add the electrons, right? So, okay, let's look at chromium, and this is chromium 3 plus. So chromium is a transition metal. So the configuration for chromium is 1s2, 2s2, 2p6. That's coming up to neon, and then 3s2, 3p6. That's the next line over, coming to argon. And then 4s1, 3d5. Remember, chromium is the one with the exception, so it pulls electrons from the s electron. Okay, so 4s1, 3d5. And so the 3 electrons that are lost are going to be one, of course, from the valence shell, which is the 4s1 electron, and the rest of the 2 electrons are going to come from the 3d. Okay, so which means that now you have 3d3. So which means what are the total number of electrons left now outside? And again, look at the shell numbers. Okay, so everything 3 is 2, 3p6, and 3d3. Okay, so 2 plus 6 plus 3, and that's equal to 11. Okay, in the third shell, so that's 11 valence electrons, and you have the 10 core electrons then. Okay, in chromium. So again, I've highlighted the I've not highlighted it yet. I will highlight these electrons for you, so you will know that. Okay, all right. So then with the fluoride here, so the fluorine configuration is 1s2, 2s2, 2p5. It's in group number 7, right? So 7 has 7 valence electrons. Fluoride would be 1s2, 2s2, 2p6, because the extra electron will come into the p shell, p subshell, because that's the, you know, unfilled one. So now what happens is that the highlighted one here, that's going to be your, I guess that is still your valence shell. And so that's your valence electrons, which is 8 valence electrons. And now you have 2 core electrons inside. Again, just take the higher number. That's going to be the valence electrons, okay, when you're trying to do it for ions. So isoelectric elements and ions. Isoelectric means that when you have 2 or more elements or ions that have the same number of electrons. Okay, so that number of electrons can be from, of course, giving or taking electrons. Okay, so for example, the oxygen here, oxygen has taken 2 electrons, fluorine has taken 1 electron, and so both of them have the same number of electrons now, which is also similar to what neon has. So these are considered to be isoelectric species. Now, what is the purpose of isoelectric species? Right now, not a whole lot, except that you need to know the term, okay, as to what it means. What happens is that some of the properties change, and physical properties we're going to do with periodicity in the next section. So some of the properties will change, and so we can ask you, okay, you know, you're looking at isoelectric elements on the third period, you know, in the third row, what are the properties of such and such, you know, and so that's something you may need to know. So isoelectric, you need to understand, is any kind of element or ions that have the same number of electrons. That's all it is. So just count the total number of electrons, not in the valence shell, not in the core, total, okay, number of electrons. That's how it goes. So here is an example for that. And so let's see what we have. Group the elements and ions that are isoelectric and give the number of electrons in each of those groups. So first of all, what you do is you just find the total number of electrons, okay, in each of them. Now, some of them are hypothetical, some of them are real, okay, and it doesn't matter. That's not a concern if something exists or not. The thing is, we're just trying to identify what has the same number of electrons. That's all it is. Okay, so if you look at C4 plus, which has given 4 electrons away, it had 6 to begin with, so now it has 2 electrons, right? That's what it means. So that's what we are trying to do here. Helium has 2, beryllium has 4, and so you find out the electrons that are in each of these species. So silicon 4 minus, which is 14, plus 4 is 18 electrons. Okay, so once you've identified all the electrons in there, then you just group them together. Okay, so the isoelectric species are these, 18 electrons are this group, 10 electrons is this group, and poor beryllium, oh no, doesn't have anything. Okay, so it's by itself, doesn't have any at least not in this group. But anyhow, that's how you group isoelectric elements or ions. One last thing I want to mention to you, so you don't think like you've never heard of this before, is a property called paramagnetism and diamagnetism. Paramagnetic substance is anything that can be magnetized, whereas diamagnetic is not magnetized, which means that it doesn't get affected by a magnetic field. Paramagnetic substance does get affected by a magnetic field. This happens, paramagnetism happens when you have unpaired electrons. So when we fill out our box configurations, that's where this is useful. Okay, so I just want you to know the term, so in case you're like, I've not heard this before, that's kind of what it is. But elements have magnetic properties, so that's where they get it from. And that's that, I guess, for this one. So all right.